Part A is the standard story about why the halogens become less volatile as you go down the group. So hopefully you've learned this in advance, and therefore this is one of the easy mark questions. So the important things are, first of all, that as you go down the group from chlorine to bromine to iodine, the number of electrons per molecule increases, because obviously the atomic number increases, so the number of electrons per molecule increases, therefore the induced dipole-dipole forces between the molecules become stronger. Okay, so you've got to make sure you specify the kind of intermolecular forces. So the induced dipole-dipole forces between the molecules become stronger, and therefore it takes more energy to break them. So those really are the three marking points. Number of electrons per molecule increases, gives you stronger induced dipole-dipole forces, meaning that more energy is required to break them, and hence the boiling point increases. Part B again is actually a very standard question, so as long as you're careful, this again is an easy one. So enthalpy profile diagram means that first of all you've got to mark on the enthalpy levels of the reactants and products, and the key thing to notice is that delta H is positive, so it's an endothermic reaction, meaning the products are going to be higher than the reactants, so make sure you get that the right way around. So we mark on a level corresponding to 2HI, always include the state symbols, because obviously the state of the substance affects the enthalpy level, so that's important. So we've got 2HI there, and then at a higher enthalpy level we're going to have H2 gas plus I2 gas. Okay, so those are the enthalpy levels, and then the idea is that we've got to mark on two pathways leading from here to there. So in the absence of a catalyst, there's a relatively big activation energy. So we're going to mark a high hill like that. And the important thing is that when you mark on the activation energy, that you get it precisely between the right levels. So if it's going to get kind of crowded there, one useful thing that you can do is to just draw a dotted line across like that, and then draw one across from the top of the peak. Just do it with your ruler to make sure it's precise, and then you can mark on the activation energy like that. It just makes it a bit less crowded than putting it in the middle. Obviously you don't have to do that, but that's a possible way to do it. So that's the activation energy in the absence of a catalyst, and if you read the question carefully it tells you to label that EA. And then what the catalyst does is to provide a new reaction pathway with a lower activation energy. So it still starts here, it still ends up there, but the height of the hill is reduced. So you're going to have something like that. And again, we can just mark the top level like that. And now the new activation energy still starts from the reactant level, but it just goes to the top of this hill. So it's a smaller activation energy, and that's the one it tells us to label EC. And that's it. That's all you need for your 3 marks. Part C, then we've got to work out the identity of A, and you can see that at the core of this problem is an ideal gas question, because it gives you the pressure, it gives you the temperature, and it gives you the volume, so you've got to therefore work out the number of moles, and because you've got the mass you can therefore work out the MR, and because you've got the MR you can deduce how many chlorines and oxygens it must be. That's the strategy. So we start with the ideal gas equation, which is this, and the thing we don't know, because we know the pressure, we know the volume, R comes from your data sheet, we know the temperature, so N, which is the number of moles, is what we don't know. So the first job is to rearrange that. So remember that that pair of terms we can just slide diagonally across and get PV divided by RT is equal to N. And then we've just got to plug the numbers in, but you have to be very careful here with units. So pressure has to be in Pascal, and it is, so that one is easy. So that's 1.00 times 10 to the 5, so that one doesn't need changing. But the volume needs to be in cubic meters, and at the moment it's in cubic centimeters. So you either have to know that there are 1,000,000 cubic centimetres in a cubic metre, so you would therefore divide by 1,000,000 to get the number of metres cubed. Or you can sort of think of it in two steps, that because you're very used to the idea that, to go from cm cubed to dm cubed, you divide by 1,000, because there are 1,000 cm cubed in a dm cubed, and it's just the same again going to metres cubed. Okay, so you can sort of remember it that way, which just means that to go from cm cubed to metres cubed, you divide by 1,000 and divide by 1,000 again, which again tells you divide by 1,000,000. So V is 76.0 divided by 1,000,000. Okay, and then R comes from your data sheet, is 8.314, and T, remember, has to be in Kelvin. So 100 degrees C, we add 273 and we get 373 on the bottom line there. Okay, so those are the numbers that we have to crunch, so we can put those into the calculator. So we've got 1 times 10 to the 5 times 76 times 10 to the minus 6, which is 76 divided by 1,000,000, divided by 8.314 divided by 373 is equal to 0.0024507 moles. Okay, so that's the first step. Make sure that number is clearly visible in your working, because that's going to get you some credit. And then we think, right, we know the moles, we also know the mass, so we can work out the MR of compound A, which is mass over moles. Okay, so MR is mass over moles, so that's 0.4485 divided by that number of moles. So divided by 0.0024507. And if we crunch that, we get 183.0. Okay, so now we know the MR. And the final thing is that it's an oxide of chlorine, so we have to figure out how many chlorines and how many oxygens will add up to 183. So you've just got to kind of do a bit of trial and error here. The first thing is that it's a whole number, and the atomic mass of chlorine is 35.5, so that tells you you've got to have an even number of chlorines, because otherwise you would get a 0.5 in that. So we know straight away it's got to be 2 or 4 chlorines or whatever. So let's go with 2 and see if that works. So we say, right, let's go 2 chlorines. That will add up to 2 lots of 35.5 is 71. If you take 71 away from that, you get 112. And you think, right, how many oxygens go into 112? So oxygen is 16, and if you do 7 times 16, you do indeed get 112. Okay, so that's the number. So Cl2O7 fits, because you've got 2 times 35.5 for the 2 chlorines, plus 7 times 16 for the 7 oxygens, equals 183. And therefore that is your answer. So part D, there's always going to be a big titration calculation in your paper 1, and here it is. So the first thing it wants us to do is to take the actual titration data, which are in the table here, and we've got to find the mean titer. So first of all, we've got to do the subtractions, which is just final minus initial. So we've got 24.00 there, 23.40 here, 23.75 there, and that one, if you subtract it out, is 23.85. So to find the mean, what we have to do is to select which ones we're going to average. And there are two very simple rules. The first one is that we never use the trial. Doesn't matter how closely it agrees, you just don't use it. And then you look at the remaining ones and you only take the ones which are most closely clustered together. So you can see in this case this one is clearly not particularly close to these two, whereas these are within 0.1 of each other. So we're not going to use that one, we're going to use this one and this one. And so the mean titer is just the mean of those two, so that's 23.75 plus 23.85 divided by 2, which is 23.80 cm cubed. So that's the first bit. Now it wants to know about percentage uncertainty. Now you've got to read the question carefully here, because the trap you might fall into is to use that volume, the uncertainty on that volume, but that's not what it's asking you, because that's the mean and you can't do that. What you've got to do is to measure the percentage uncertainty on an individual experiment, and the one it asks you about is titration 1, so that is the volume that's relevant. So percentage uncertainty is just equal to the maximum error divided by the value measured times 100. Okay, so you need to know that definition, and it tells you that the maximum error, the uncertainty on each burette reading is 0.05 cm cubed. Could be bigger, could be smaller, that's what the plus or minus means, but that doesn't matter. The maximum error is 0.5, but it's that on each reading. And what you have to remember is that in a titration, you read it once at the beginning and once at the end. So each of those measurements has an error of 0.05. So the maximum error is 2 times 0.05. So anytime you have a measurement which involves 2 individual values going in, so initial and final values in a titration, or maybe mass of the beaker plus compound minus mass of the beaker on its own, again 2 individual measurements, you have to add up the uncertainties on each one. So 2 times 0.05 divided by 23.40 times 100. So if we compute that on the calculator, it comes to 0.4274%. But you've got to read the question carefully. It says it wants it to 2 decimal places. So that means we've got to round there. So that's 0.43% to 2 decimal places will be the answer. In the next bit, it's asking us about what you actually do during the titration. In other words, how you tell when you've got to the end point. So remember, what we're doing here is in the first part, before we start the titration, we're doing this reaction at the top which produces iodine. So in our flask, we've got aqueous iodine. And what we're doing is from the burette, we're adding sodium thiosulfate. So it's always a good idea just to picture the titration and think, right, that's going to be brown. So in principle, what you do is you look for the moment when the brown colour disappears, because as the iodine's used up, the brown colour gets paler. But the problem is that when it gets very pale, it's actually hard to see. So what you do is you add starch as an indicator when you get near the end point. Okay, so when you get close, in other words, when the pale brown colour's got quite pale, you add starch solution, and that turns it blue in the presence of iodine. And then you keep on titrating, and when you use up the last of the iodine, there's no more blue complex there, and so it turns to colourless when all of the iodine has been used up. So the end point is when the solution turns from blue to colourless. So to get the marks, you had to talk about adding starch near the end point and then look for the point where it changes from blue to colourless. So now finally, after all those preliminaries, we get to the big calculation. So it's a titration calculation, so what we're going to expect is that we're going to start with moles is concentration times volume in dm cubed, because that's what titrations are all about, is measuring the volume of something of a known concentration, so you can do that calculation. And of course in this particular titration it's the thiosulfate whose concentration is known. Sorry, that arrow's in the wrong place. It's that, which is 0.15 moles per dm cubed. So we know the concentration of that, and we also know the volume, because that's what this is. This was the volume of thiosulfate that needed to be added to just use up all of the iodine. So that's equal to 0.15 times 0.0238. Okay, dividing that by 1,000 to put it in dm cubed, which is 0.00357 moles of thiosulfate. And then, as always, what you expect in a titration calculation is that you have to consult the equation to relate that to moles of the other stuff, because obviously it's the iodine we're actually interested in, because it's the iodine that was produced by this reaction, which we can then relate back to the IO3-. So the next job is to say that from the equation, moles of iodine, and you can see it's just half as much, is a half of the moles of thiosulfate, because that's what that equation tells you. So we just divide that number by 2 and we get 0.001785 moles of I2. Okay, so that was the mean amount of iodine that was present in each titration, and that iodine was produced by this reaction. Okay, and since we had excess iodide, it tells you that in the method, the amount of iodine that was there is controlled by the amount of IO3-, and that's the principle of the method, that this is now going to enable us to work out how much IO3- was added in each individual sample. Okay, so we've got that 3 moles of iodine comes from just 1 mole of I-. So again, this is from the other equation. Okay, so from the other equation, moles of IO3- is equal to 1/3 of the moles of iodine. Okay, because 1 IO3- goes to 3 I2, so we can divide that number by 3, and we get 5.95 times 10 to the minus 4 moles of IO3-. Now, that's the amount of IO3- in each individual titration. In other words, in a 25 cm cubed sample. Okay, so that's in a 25 cm cubed sample. What we now need to know is, well, what's the total amount of IO3- in our 250 cm cubed? Okay, so the total moles of IO3- in 250 cm cubed is 10 times the moles in 25 cm cubed, because obviously it's 10 times bigger volume, which is just 5.95 times 10 to the minus 3 moles of IO3-. So now we know, because it tells us in the question that it's a group 1 iodate, so the formula of the compound will be MiO3, right, where M is our mystery group 1 element, because we've got a 1- ion and we know group 1 are 1+. So because of that we can say that the moles of IO3- is equal to the moles of MiO3. So we know the moles of the compound, we also know the mass, because it told us in the question. So we can therefore work out that the MR of MiO3 is equal to mass over moles, which is 1.55 divided by this number, 5.95 times 10 to the minus 3. And if you work that out, that comes to 260.5 is the MR. So now all we have to work out is what M must be in order to add up to that. So we can work out that IO3 has an MR equal to 126.9 for iodine, plus 3 lots of 16 for oxygen, which adds up to 174.9. And if we do the subtraction, the total MR, 260.5 minus 174.9 is equal to 85.6. And that's very close to rubidium, which is a group 1 element, which comes in at 85.5. So that tells you that M is rubidium, and therefore B is rubidium iodate, RbIO3 is the answer.